Hi, my name is Avi Shah, and welcome to this online lecture on enhanced control strategies. In this video, I will go over Cascade control, which is an improved form of feedback control that allows response times to disturbances to be reduced. Before we get into how Cascade control works, let's think about why we want to use it over a conventional feedback control system or a feed-forward/feedback system. The first main disadvantage to feedback control is that it becomes inefficient for systems with large dead times. Dead time is the time it takes from when a sensor measures a change in the control variable and sends a signal to the manipulated variable up until the controlled variable begins to respond. In this case, a feedback control system will take a while to return to steady state. Another main disadvantage to feedback control is that it becomes inefficient with a system with continuous disturbances. Here, when the system dead time takes a similar amount of time as the time interval between when disturbances occur, the control system becomes inefficient. For example, a disturbance is detected and the system changes the manipulated variable to account for the disturbance. But as soon as the response is noticed, another disturbance enters the system, throwing off the control still occurring for the first disturbance. This puts the system at a risk for oscillation, where the measured variable will never reach the set point, leading to an inefficient process. Now looking at the disadvantages of a feed-forward/feedback control system. Now, the system is inefficient if the model predicting the system's behavior is not accurate. This may be an issue in complex systems where modeling the entire system accurately is not possible without putting in large amounts of time and resources. This issue is made worse in complex systems with many disturbances where a feed-forward model needs to be designed for multiple components of the system. Doing so requires the feed-forward control system alongside a feedback control system for safety, and would end up costing more and possibly being less reliable due to its complexity. Nowadays, processing plants have become more and more complex in order to increase efficiency and to reduce costs. To do so, more reliable control systems that are less complicated are required, and that's where the utilization of a cascade control system can benefit the process. So how does cascade control work? Cascade control introduces a secondary measured variable alongside the main measured variable of interest. This allows the system to detect and correct disturbances in that secondary variable long before those disturbances would make their way through the system and be measured by a change in the primary measured variable. The secondary measured variable is often the manipulated variable of the system because in the case of a random disturbance, adding the second measured variable here can correct for changes in the manipulated variable and help stabilize the process. This increases the response accuracy and removes ambiguity in the manipulated variable by ensuring that when the system calls for a certain amount of change of manipulated variable, that amount is truly delivered without disturbances in the manipulated variable affecting the response. Through cascade control, the control system can more accurately correct disturbances in the manipulated variable itself, or the combination of disturbances in the manipulated variable and disturbances in another variable. This is done using a feedback loop nested in another feedback loop. Here it is important to note that cascade control relies only on feedback systems, which reduces its complexity, allowing the control system to be more reliable and less costly to implement and maintain. Now let's go through an example that details how a cascade control system can be implemented to help us understand how it works. First, we'll go through an example of feedback control and how it differs from cascade control to help us understand the concepts. Remember, cascade control is just an improved version of feedback control. Okay, so here we have a furnace that heats up an oil feed using a feed of fuel gas. Now here we have a conventional feedback system that measures changes or disturbances in a single controlled variable. This variable is usually the component of interest, which is the hot oil temperature in this example. Here, a disturbance such as the fuel gas feed, for example, is introduced into the system, and the controller detects this disturbance through a change in the variable of interest, which is the hot oil. Doing so takes time for the process to carry the disturbance through the system and to the outlet where it can be measured as a change in the hot oil temperature. Feedback control will now adjust the fuel gas flow rate continuously until the temperature of the oil returns to the set point. However, returning to the set point will take time as the system adapts, and it may overshoot or undershoot the disturbance, requiring further adjustment. As you can see, this process will take a long time for the control variable to reach its specified value after a disturbance. And in the case of multiple constant disturbances, it may never reach its set point or oscillate around the set point. So the solution to this is adding another control system. In this case, we will add a secondary control system that measures and controls the fuel gas feed pressure. This figure shows a cascade control configuration for the furnace, which consists of a primary control loop utilizing TT, temperature sensor, and TC, temperature controller, and a secondary control loop that controls the fuel gas pressure via PT, a pressure sensor, and PC, a pressure controller. The primary measurement is the hot oil temperature that is used by the primary controller, TC, to establish the set point for the secondary controller, where the secondary measurement is the fuel gas pressure. This is then transmitted to the controller, PC. Now, if a disturbance in the fuel gas feed occurs, the pressure sensor will be able to sense the disturbance without the disturbance having to pass through the entire system. Instead, the disturbance will be directly measured and accounted for within the secondary loop. Now, the system will still be able to react if the hot oil temperature changes for other reasons, because the primary control system is connected to the secondary control system. But the overall system will be more robust because disturbances in the fuel gas feed will be mitigated, which will speed up the response to any disturbance. This will allow the hot oil temperature to reach its set point faster and reduce oscillations in the system when the fuel gas pressure is continuously fluctuating. This control system can be further improved by adding a third control loop to the system that measures and accounts for deviations in the cold oil feed. If a deviation in the cold oil is detected, the system will send a signal to the fuel gas feed to correct the deviation before the hot oil sensor picks up the deviation. However, because the cold oil and the hot oil flows are a single pipeline, deviations in the cold oil temperature will not take long to reach the hot oil sensor, making a cold oil control loop not as beneficial as a fuel gas feed control loop. In this case, depending on how tightly controlled the system needs to be and the budget for the system, the designer can choose to implement a third control system for the cold oil inflow. Now, the two feedback control loops are nested, where the secondary control loop is located in the primary control loop. And this can be seen as the set point enters the secondary control loop. And we'll go through this later in another example. And here it is actually. So here's a block diagram of the cascade control system presented in the previous example. This is something you can set up in Simulink to model the system response to disturbances. In this system, YSP1 is the set point of the hot oil temperature, and YSP2 is the set point for the fuel gas pressure. E1 is the observed error in the hot oil temperature, and E2 is the observed error in the fuel gas pressure. These errors are created by disturbances D2 and D1. D2 is the fuel gas feed, where GD2 is the transfer function that models the effects of disturbances in the fuel gas feed on the system. D1 is the oil feed, and GD1 is the transfer function that models the effects of disturbances in the oil feed on the system. These disturbances are measured by sensors whose transfer functions are GM2, and this relates to the fuel gas pressure, and GM1, which relates to the hot oil temperature. The difference from the set point is calculated at the two summation points here and sent through the controller, which is here or here, primary or secondary, and then through GV, which is the valve, and through the system model, GP2 and GP1. Each of these are transfer functions describing the behavior of each component of the system. GP2 is modeling the system's pressure feed, and GP1 is the oil feed. Here we can see the secondary control loop, which controls fuel gas pressure, is nested within the primary control loop that controls the hot oil temperature. This system allows for disturbances in the fuel gas pressure to be recognized and corrected without having to travel through the entire system. They're just enclosed in the loop here. This ends up speeding up the response the system has to a deviation in the fuel gas pressure. It's important to note that because the secondary loop is nested within the primary loop, the secondary loop must have a higher gain than the primary loop. Otherwise, the system is at risk of instability. Okay, now let's take a brief look at how we can derive transfer functions for the system. Let's try to find y1 over d2 by assuming that there is no disturbance in the oil feed, y is p1, and there's no disturbance in the oil feed, d1 is equal to 0, and that the hot oil temperature set point is equal to 0, y is p1 is equal to 0. Here we can see that y1, the hot oil temperature, is equal to y2 times gp1 plus 0 here, where y2, the fuel gas pressure, is equal to gd2 times d2 plus gp2 times gv times gc2 times e2. Now here E2, the air and the fuel gas pressure, is equal to gc1 times E1 plus gm2 times y2. And now here E1, the air in the hot oil temperature, is equal to 0 because YSP1 is 0 minus gm1 times y1. Now, if we substitute all the equations, leaving only the variables y1 and d2, we get the transfer function relating y1 to d2. Here is that transfer function, and below are transfer functions relating other variables that were derived using a similar process. In the denominator of the first three transfer functions, all of which model the process output y1, we can see the characteristic equation for cascade control in the denominator. Now here's that characteristic equation again, which is shown separate from the transfer function. Now, if we remove the inner loop by setting the transfer function for the inner loop gm2 equal to 0, then the second term in the characteristic equation drops out, and we get the characteristic equation for conventional feedback control systems. So we can see how cascade control and conventional feedback control are very closely related. It's just one term here that's being dropped out. Finally, I want to note that cascade control uses the secondary control loop to speed up the response of the system, keeping in mind that the gain of the secondary loop must be higher than the gain of the primary loop to prevent instability. When the secondary loop responds faster than the primary loop, the cascade control system allows for a larger gain in KC1 in the primary loop, which improves the overall process response. Thank you for watching.